Get started from where we left off last time. We were talking about the stuff towards the end. We talked about the interleaved converters. I mean, you sort of see what the objective of the interleaved converters is. Again, I'm not, there's nothing new in the design of the interleaved converter. You should treat them as two separate parallel converters, right? The nice thing is you get less ripple with the same output capacitor value, right? So the capacitor did not change. But because you've split the inductor current into two inductor currents and phase shifted them apart, you were able to use two small inductors, not increase the size of the capacitor, and get less ripple. But at the expense of an extra switch and a diode, of course, right? So nothing is free, right? But maybe these are small, right? A switch and a diode can be together in a small surface mount package versus a capacitor of a few hundred microfarads is probably big, right? So if size is a consideration, maybe go with something like that, for example, right? This is just an example of where you would want to use something like that. And you can apply it to all the converters that we did. Basically, you would just be paralleling inductors. So the inductor current ripple would be reduced in this fashion, yeah. Right? So they show you how to apply it here and here. Again, the analysis of this is, not something we will go through. There's nothing different between this and two individual buck converters, or two individual boost converters, or two individual buck boost converters in parallel. I just want to show you the concept of interleaved operation. I will not give you a quiz on analyzing an interleaved converter control system, for example, right? From you, they're two independent converters operating in parallel, right? This is a L switch diode and its capacitor. L switch diode and its capacitor, same thing. And the load just happens to be the same. So the inductor current is being split in half. Inductor current is being split in half in both cases. Yeah. Before I go to switching losses, let me quickly go over this control stuff, control modeling that we did, that I was talking about last time. Nothing wrong with what we did last time. I just want to go through the material quickly again to show you how similar. The similarity between the AC and PEEP nodes that you have in the textbook. So I read the material they have in the text about this. They just have 4 or 5 lines on page 259 about what I spent maybe a half an hour or so in the class about. So they describe the average model starting 254. They show you how to derive the average model for the buck converter on page 255, and that's it. And then they say, okay, then you apply it to the boost and buck boost, right? So they don't really show you how to do that, and they don't tell you that the polarities of the voltages and currents that they have in these circuits, in this let's see, this block that they have here, in this block, the polarities of these voltages and currents can change depending on the topology, right? So they don't describe that, and they don't tell you how to derive it, right? So let me just go through them quickly again, and we'll make sure that we understand how they relate to this, and then we can continue with the switching loss stuff. So first we'll do the buck converter. Buck or step down converter. So again, I have my power supply here, and I'll show you how to check your answer as well. Okay, I'll show you how to check your answer here. So hopefully that will be helpful. So we have our MOSFET, our diode, our capacitor, and our resistor here. Again, what is this current? They call this IC. ICIL doesn't really matter. They call this IC, and they call this node C all the time, right? And this is your V output, and this is your V input. When the switch is closed, what is switch current? Come on, this should be quick. As a proportion of inductor current IC. Yeah, when the switch is closed, it's IC. So what is the average value? Sorry, what's the average value of switch current? Sorry. Well, why are you saying half? It depends on the duty cycle, right? It's D times IC. right? How about the diode current? 1 minus D times IC. These are the average values of the current. So now if I ask you to select switches, you would select switches based on peak voltage and average current, right? That's the first component that you would select. Peak voltage across this switch is what? You say this is open, this is closed, right? If this is open, this is closed, what's the voltage across the terminals of this switch? Vin, right? So the peak voltage across the switch is Vin, the average current is D times IC. IC here, the average value happens to be the same average value as the load current average value, because capacitor does not, the average value of current, average current does not flow in a capacitor, right? So from your knowledge of the load, you should know the average value of IC, you should know the average value of switch current, you should know the average value of diode current. From the circuit topology, you should know the peak voltage across the switch, peak voltage across the diode. Short this is open. What's the voltage across the diode? V input as well, right? So you have peak voltage and average current across the switches now. So we have these. Now I want you to tell me what the voltage is across the switch and the diode for now. What's the voltage across the diode? What's the average voltage? What's the average voltage across the diode? So what would we do? We look at the diode when the switch is closed. When the diode, we looked at these points. This is the voltage across the diode. We look at the voltage across these points, across these 2 points, when the switch is open and when the switch is closed, right? So when the switch is closed, the diode is open. So what is the voltage across the diode? Average value, yes, it's dVn, right? Because when the switch is closed and the diode is open, the diode voltage is D, right? So it's D for the duration of the switch being on. So the average voltage across the diode is D times Vn, right? So the average voltage, this between these 2 points is D times Vn. How about the average voltage across the switch? Exactly, right? Because again, Kirchhoff voltage law, this plus this plus this, in an average sense, have to be equal, right? So this is the voltage. This voltage is 1 minus D times Vn. Now I have the voltages and currents across the diodes and switches and everything, and the currents across everything I need basically to draw my next equivalent circuit, which is what they have, the average model equivalent circuit, right? So here, this circuit has switched waveforms. All of these waveforms are, we said that when the switch is on, the voltage across the diode is Vin. Switch is off, it's 0. Vin, 0. Vin, 0, right? That's what we said, is the voltage here. And here it's the complement of that, correct? Across the switch, it's the complement of whatever's across the diode. So all these are switched waveforms. Switched waveforms are, from a control perspective, a nonlinear phenomenon. So this circuit behaves in a nonlinear fashion. We cannot model this as a linear time invariant system. So to model this as a linear time invariant system, we have to convert this circuit to something equivalent in an average sense, because our waveforms at the end here are waveforms of interest, are really what's happening here, right? And all of these waveforms are continuous waveforms, right? So we said, okay, if I have properly chosen my inductors and capacitors such that across the switching period, the ripple current is small and the ripple voltage is small, that means that my waveforms are pretty much continuous, right? That's what it means. So if I'm assuming that my waveforms are pretty much continuous, then let me look at the average values of the voltages and currents around the system and come up with an equivalent representation of the circuit. And leave in the L's and C's in this equivalent representations so that I can look at the dynamic response, so I can design a proper controller when I study the 420 course, the linear control systems course, right? Because there, if you don't have a dynamic behavior, then you don't design a controller. Then it's just steady state behavior, right? And you are going to look at steady state behavior. Even in 420, you look at steady state behavior, right? And then you also design a controller for the dynamic response. You consider that as well. So let's see how we consider both of these in our circuit here. So I will redraw the circuit, and I will just put two dependent sources. Again, the voltage, the current through the switch depends on the inductor current. The voltage across the switch depends on the input voltage. So I can put a dependent voltage source or a dependent current source. But I'll put something here. I'll leave it empty for now. And then I'll put something here. I'll leave it empty for now to represent now my two switches. Right? And then I will keep in my inductor and capacitor and resistor. Right? This is IC. This is V in. This is plus minus V out. Right? They are trying to generalize what you put in this block as always the average value of the inductor current. So there will be one node will have a current source that will have a value equal to the duty ratio multiplied by the average value of inductor current. Okay? And the other node will have a dependent voltage source that will equal the average value of the input voltage across the two switches, which is the VAP, right? So let's see where that is satisfied in our circuit, right? So one node will have current flowing through it, meaning a current source represented there, and that current source has to have a value of duty ratio times the average value, duty ratio times the value of inductor current, right? So let's see what node I can use, I can do that with. So which node has a value of current equal to the duty ratio multiplied by the inductor current, or the current in the other terminal? This one. So let me put this as the current source. This current source has a value of D times IC. Right? And this would be node, this is node C according to their, node C according to the box that they had. Right? And this would be node A according to the box that they have. And then here I would have a voltage source equal to duty ratio multiplied by the voltage across the two switches. Right? Where is the voltage across the two switches? The voltage across the two switches is this voltage. Right? So it's D times V input. So this is the voltage source, D times V input. How do you check your answer? Somebody tell me. You know for the buck converter, what is the relationship between input and output? V output is equal to the buck converter. D times V in, exactly. We know this is the relationship that we derived from the equations in the slides, right? And we have the equation for the boost and we have the equation for the buck boost, okay? Now, I want you to check your answer. In steady state, this equation is a steady state equation. Does this have any dynamics? Does not have any dynamics, so it's a steady state equation. For steady state DC, what does the inductor look like? Short circuit. For steady state DC, what does the capacitor look like? Open circuit. So I short circuit my inductor and I open circuit my capacitor. I redraw the circuit here. Short circuit my inductor, open circuit my capacitor. I draw the circuit this way. This is V in, this is V out, and this is D times IC, this is IC, this is plus minus dV in, right? This should be the steady state circuit model, right? So how do I know I'm correct or not? I need to make sure that this is satisfied. So what is V output equal to? Exactly, they're parallel. This is parallel to this. So V output is equal to dV in. Okay? So that means I'm satisfying this, so this is a good model. This is a steady state version of it, this is the dynamic version of it. So now, if you're going to go and design a controller for 420, you take this circuit and you start playing with it. Then you try to do Kirchhoff voltage law around this loop, around this loop, around this loop in the S domain, the Laplace domain, and you have the Laplace domain representation of the circuit, and you can find the relationship between, input duty ratio, for example, and inductor current, or duty ratio and capacitor voltage. Okay? Okay with this? We'll do the same quickly with the, so then this is C, this is A, this is what they call P in the textbook. Okay, but, and then it's the same polarity for the buck converter. The boost converter, they flip, the polarities are flipped. So let's look at here. The A is where the current source is, P is where the voltage source is, C is where the conductor current is. A and P. So A is where the current source is, P is where the voltage source is, C is where the inductor current is. Right? The boost converter here is the current is flipped, right? The current is going into C. Here it's coming out of C, right? So if you look at this, current is coming out of node C. Here actually current is going into node C from the boost converter, right? So they didn't explain that in the textbook. So, and I didn't read that. I mean, I hadn't read that section in the textbook before coming to class, so I didn't know that it wasn't explained properly. So what we will figure out a way to put this circuit in this box, but the polarities will be flipped. Okay, that's what I should have said last time. So everybody's okay with this? The process will be similar. We'll do this circuit, we'll do this circuit, we'll do the average model, and we'll make sure it satisfies the voltage transfer equation. That's exactly what we'll do. Then it's 420. That's what you do for 420. But this stuff is very important for selecting your components, right? Because after we did this, you know what the average current through the switch and the diode is. And you know what the peak voltage across the switches are, right? From here, you know that stuff, yeah. Okay. So now let's do the boost converter. Okay. For the boost, we have our voltage source here, our inductor here, our switch here, our diode here, our capacitor here, our inductor here. This is my V output, this is my V input, and this is what? IC according to the model that they're using. So this is this node C that they're talking about, okay? So we always have C quickly. And the voltage transfer ratio for the boost converter is what? V output is equal to V input 1 minus D, right? If you go back to the slides, that's the input to output voltage relationship. Yeah. Now we'll go through the same process. We'll see what the average values of currents and voltages are across the switches, and which one is DIC, and we'll use that as the current source. The other one will be the voltage source. Same process. Okay. So now when the switch is on, what's the average value of switch current? So when the switch is on, it carries inductor current, right? When the switch is on, it's carrying inductor current. When the switch is off, inductor current is flowing through the diode, right? So when the switch is on, it's carrying inductor current. So what's the average value of current through the switch? Exactly, it's D times IC, because when the switch is on, it carries IC current. So the average value of that waveform is D times IC. Then the average value of diode current is 1 minus D times IC. So obviously here is where we're going to put the current source, right? And then here we'll put the voltage source. So we need to find the voltage across the diode. So what is the voltage across the diode? So when the switch is on, the voltage across it is 0, right? And the voltage across the diode will be V output, V in plus V inductor, or just easily, if this is a short circuit, and it's going to be V output, right? This is 0, and then so the voltage across the diode will be equal to V output in this case. What? Because when the switch is on, the diode is off. So this is an open circuit. Kirchhoff voltage Kirchhoff voltage law around this loop. This is 0, because I'm assuming it's a lossless switch. So the voltage across the diode is equal to the voltage across the capacitor, which is equal to the output voltage. Okay? So diode voltage is equal to, average value of diode voltage is equal to what? When the switch is on, the diode has a voltage across it equal to the V output. So what is the average value of diode voltage? Exactly. When it's on, when the switch is on, meaning for duration D, the diode has a voltage across it equal to V output. And then when the switch is off, the diode is short-circuited. Because it's on, so it has a voltage across it of 0. So it's V output 0, V output 0. Right? What's the average value of this waveform? D times V output. Right? We said for a square wave, it's always D times V output. Okay, so then the average value of voltage across the diode is D times V output. So we have our D times IC here, and we have D times V output across, this is my voltage across the diode. It is equal to the capacitor voltage, which is equal to the output voltage when the switch is open. Its average value is D times V output, because its voltage V output exists on it when the switch is on. Okay, so now I have my D times V output. V output is the voltage across the two switches, right? So this is the AP nodes that they're talking about in the text, right? So it's always the voltage source value is D times the voltage across the two switches. In the buck converter, it happened to be the input voltage. In the boost converter, it happened to be the output voltage. In the buck boost, it will be the input minus output. Okay, so it's the output voltage. So now I can draw my current source and my voltage source. Right, so I redraw the circuit, put two dependent sources, and figure out which is my current and voltage source. This I represent as a dependent source. This I represent as a dependent source. And I put my L's and C's because I would like to design a controller that takes care of the dynamics, right? Currents flowing this way. This is the polarity of the voltage source. The voltage source has a value of D times V output. Current source has a value of D times IC. This is IC, this is V in, and this is plus minus V out. Okay? In steady state, I have to satisfy this, correct? I always have to satisfy this in steady state. Steady state, I redraw the circuit with the L as a short circuit and the C as an open circuit. Right? So now, let me do Kirchhoff voltage law. I would like to make sure I'm satisfying this. This one is not as clear as the buck converter, right? So here I have to do Kirchhoff law, the voltage law on the circuit to make sure I get this equation. See, I'm actually getting these equations without even deriving all this stuff that they had in the textbook, right? This is a much better way to do it. And for me, this whole chapter on with all these equations you can throw away. Again, you don't need to for the exam. You should use them. But as an engineer, if you understand this, then you don't need to do any of this equation business here. So now let's see if we're correct. So Kirchhoff voltage law around the loop. So this voltage source plus this voltage source has to equal V output. Because here I have a current source. Current source, remember, how are you playing with current sources? Your current source with an impedance in parallel is equivalent to a voltage source with an impedance in series. Right here, I don't have an impedance in parallel that I can play with. I can maybe put as an open circuit, and then the representation of this would be a voltage source in series with a short circuit. Right? If this is a current source with an open circuit in parallel, then the representation of it would be a voltage source with an impedance zero impedance with a short circuit in series. So you can do it that way, but it's easier to find the loop without the current source, right? So here, this is a loop without the current source. So V input plus D times V output is equal to V output, correct? So I want to bring V output on one side, so V output times 1 minus D, right? And bring this to the other side. So V output 1 minus D equals V input, so V output equal to V input over 1 minus D. So I know I'm correct. Okay, now we'll do the buck boost. Again, same thing here. If you want to design everything, you know the average value of current in the switch, you know the average value of current in the diode, you know the peak value of voltage across the switch and the diode. Peak value of voltage is what? Right? The peak value of voltage across the diode is V output. Peak value of voltage across switch is V output as well in the boost converter. Right? So your peak value of voltage and average value of current. So if you were to select switches, you can do that. Right? Not considering switching losses. We still didn't talk about switching losses. We'll talk about switching losses next. And then capacitors and inductors, we know how to, we draw the waveforms, so we know how to select them, the inductors and capacitors. Right? Okay? From the waveforms, we can select the minimum value of inductor and capacitors to satisfy my current and voltage ripple specs. And then I have to go and consider real capacitor inductor selection. Real capacitor selection, I go with my peak voltage across the capacitor and RMS current, because I have ESR. So you consider the I squared R and you consider the peak voltage. In addition to the minimum value of capacitance that satisfies your ripple. Right? So these are the three components. For inductor, you've selected the minimum value of inductor that satisfies your current ripple from the waveforms. And then you have to make sure when you go into the data sheet, you make sure you're satisfying your maximum current spec as well as your I squared R spec. Okay? So that's the so let's see which so this is obviously node C, right? And then this is node A is where the current source is, right? Current source, yeah, they call it A, and this would be node P. So CPA for the boost converter, CPA for the boost converter. Okay, just that all the polarities were flipped. Sorry, the C was going out, the voltage polarity was flipped, so that was a bit confusing. Yeah. Buck boost, same philosophy. So we have our buck boost converter, we draw the circuit, we have a switch here, we have our diode, we have our capacitor, our resistor, and our mighty inductor. This is my V output, this is my V input, this is my IC. Okay, so this is node C, or node C, sorry, they put it here before the inductor, sorry. Okay, so this is node C here before the inductor. Yeah. Now I want to see where node A and P is, right? So same philosophy, right? I go and look at, and what's the voltage transfer ratio for the buck boost converter? V output is equal to negative V input D over 1 minus D. That is what we want to make sure we satisfy in a steady state, right? So same process, right? When the switch is on, the diode is off. So this is an open circuit. So when the switch is on, it's carrying the inductor current. So what is the switch current? Average value? D times IC. Okay, so we found one of the nodes. Then the other node, we have to find the voltage. But of course, it's always good to know the average value of current in a switch in the diode, because you're going to select the diode. So the average value of current in the diode will be 1 minus D times IC. That's the average value of current. Now you want to find the voltage across the diode. Right? So we found the current, so we can now have the current source. We want to find the equivalent voltage source that we're going to stick in the circuit. Okay? We said that the value of the voltage source will always be D times the voltage across the two switches. What is the voltage across the two switches? Two switches are here, right? The switch and the diode, sorry, I call it this way. I mean, it's a switch, right? So what's the voltage across the switch and the diode in this case? V in minus V out, right? It's V input minus V out, right? So the volt, and let's look at it. I mean, when the switch is on, the diode is off, right? When the switch is on, it's connecting V in to this point, right? And I have V out here. So across the diode, I have on one side V in, on one side V out, right? So the voltage across the diode is V in minus V out when the switch is on. That's why it's D times V in minus V out, not 1 minus D, right? It's because the V in minus V out appears across the diode when the switch is on. So now I redraw the circuit with my two sources instead of the two dependent sources, instead of the two switches. And I stick my inductor here to analyze the dynamic response. Current source. This is D times IC current source, and this is D times V in minus V out voltage source, and this is IC. So this is node C, this is node A, this is node P. Okay. Again, the polarities are flipped because IC current is actually coming out. Right. So that's the only thing is the polarities. Okay. So just need to make sure take care of the polarities issue. And then again, same business. Steady state. Inductor is what? Steady state. Short circuit. Capacitor is an open circuit. So I redraw my system with the inductor as a short circuit and my capacitor as an open circuit. So this is my new equivalent circuit. Okay. This is easy in this case because now I would like to find the relation between input and output. So this is this voltage here, and I assume this is my polarity of my V output, so I have to stick to it. If it becomes negative, it's negative, right? But this is what I've always assumed as my polarity because I said it's the voltage across the diode is V input minus V output. So I did not say it's minus negative V output. So I kept it as a polarity. I kept the polarity in this fashion, right? So Kirchhoff voltage law around this loop says that this plus this equals 0 or this equals negative of this, right? So D V input minus V output equals minus V output, right? So D times V input minus V output is equal to negative V output from Kirchhoff voltage law around this loop. Okay, these two are equal to each other, negative of each other. Yeah. And then I want to V output on one side, so let me multiply by a -1 here. So this becomes positive, right? And then this is negative, and then this is positive, right? And I have minus D times V input plus D times V output equals V output. So I can bring D times V output onto one side, and I would have minus D times V input equals to V output 1 minus D, right? So I have V output is equal to minus V input D over 1 minus D, which is the same thing we had up here. Okay? So, is it clear? And now we have also the average values of voltages, the average values of currents in the switches and the peak values of voltage across the devices. Because we said that this device will have a voltage equal to V input minus V output across it when the switch is on. When the switch is off, it will be, when the switch is on, When this switch is on, the switch will have 0 volts across it, but the diode will have V input minus V output. And then it's vice versa. The switch will have V input minus V output because the diode is on. When the diode is connected, it brings V output to this node, so the switch will have V input minus V output across it, right? If the diode is on, it brings V output voltage here. So the switch will have V input minus V output as well, right? So the switch and diode peak voltage ratings are V input minus V output. Their average value of current we have here, D times IC or 1 minus D times IC. Where would you get this from? It happens to be that 1 minus D times IC is also equal to the average value of load current, right? Because the average value of load current is going to flow in the diode. So it's 1 minus D times IC is the average value of load current. So if you have the load specs, you should be able to tell me, and if you have the load specs, and you're typically going to have also your source specs. I tell you have a 1 volt battery, and I want you to boost it to 5. So you have V input, and you have V output. That means you have D. If you have D, and you have the value of average load current, because you know your load is consuming 5 watts. So you have the output voltage across the load, you have the current through the load, average current to the load. Average current to the load is equal to the average diode current as well, which is equal to 1 minus D times IC. You know D, that means you know inductor current. Right? If you know inductor current, that means you know switch current. Right? So it should not be a problem to design, to select the switches. Just the first selection. Then if I tell you, okay, then tell me what's the highest switching frequency you can operate at. You cannot do that yet. We have to consider switching losses, right? Because we have rise times, we have fall times, and we have losses, right? So 2 considerations. The rise times and fall times have to be, a lot less than your switching period, right? Because if your rise times and fall times are almost equal to your switching period, then you cannot control duty ratio, because by the time you rise and by the time you fall, you're done. You're not. I mean, this is your switching period, right? So the ratio between your rise times and fall times, let's say they need to be at least, for example, there's no right or wrong answer, right? But they should be at least, maybe 1/10 or 1/20th of your switching period, because that way, if they're 1/10 or 1/20th, then you have time to rise, fall, and then put some duty cycle in there to control the duty cycle, right? So, I mean, there's no right or wrong answer, but I mean, there's no right answer, but there's definitely a wrong answer, right? So there's a wrong answer, because if your rise time and fall time, rise time plus fall time, is close to your switching period, you have no control. You will not be able to control your duty cycle to be 80%. You cannot. Or you cannot control it to be 10%. You will not. By the time you rise, you will fall. So you will have a small duty cycle, and that's it. You cannot increase that duty cycle. I mean, there's no way. You don't have control in that period at all, right? So there is a wrong answer, but there's no right answer. But there are many right answers, unless I put another constraint, right? Which is loss, right? I can put a constraint that's loss. I can put one constraint can be switching frequency. In this case, if I don't put an additional constraint, there can be many, many right answers. If I put another constraint, which is loss, then what can you do? You have to make sure that your rise times and fall times are a lot smaller than your switching period. That's one. So if you do that, you've selected a switching frequency range that you should be operating, okay, beyond, right? So, if I cannot increase beyond, I cannot make my switching period less than a certain amount, because my rise times and fall times are going to be now as big as my switching period, okay? So that's one consideration. That has limited your switching period, which means it sort of put a limit on where your switching frequency needs to be. You cannot operate greater than the switching frequency. You have to operate less than that, right? But we will see that there is a relationship between switching frequency and losses. So if I tell you now, also make sure that you limit the losses to a certain amount. Then, okay, you've selected, you know that you can operate in a certain range of switching frequencies. Part of that range will cause too much loss, right? So you cannot operate in that range as well. So you tell me, no, the range is this. Again, there will be lots of right answers. There will be not, but there will be definitely wrong answers. Lots of right, but definitely clearly some wrong answers. That's assuming I give you data sheets, right? So I'm talking about, I give you several switch data sheets, and you look at the rise times and fall times, and you look at switching frequencies and stuff like that, and losses, which we will do right now. So, but you have to be able to calculate average values of currents to be able to select the switches. Okay? To start the selection switches. Now, so that's hopefully we took care of this. Everybody's okay with this now? The rest is 420. The rest is what you need to do in 420 or what you ended up 214 talking about. Let's do the switching loss stuff. So we said that if when a switch is turning on, time is needed for the switch current to rise, and time is needed for the switch current to fall. It's not zero. It's a finite amount of time, and we saw in the data sheet. Can be nanoseconds, can be microseconds, right? Can be milliseconds for the very, very high switching, very high voltage switches, right? So it's dependent on the switch. You have to look at the data sheet. Typically, for the higher voltage switches, it will be more. Typically, if you compare MOSFETs to IGBTs will be more. Higher time, more time to rise, more time to fall. IGBTs will also have more time to fall than more time to rise. From the physics of the device. Again, we're not discussing device physics, and I'm not an expert in device physics, but fall times in IGBTs are longer than rise times. It does take more time for you to be able to block again in an IGBT versus a MOSFET. MOSFET channel, controlling the MOSFET channel is very different than the depletion layers in the bipolar structure of the IGBT, right? So you have a gate. The IGBT has its gate is a MOSFET-like input gate, but its actual path for power flow is like a bipolar junction transistor. So it depends on having these depletion layers, and you charge and discharge the particles in the depletion layers and the electrons and holes and all that business. Again, I'm not an expert in that, but it takes more time to turn it off. So you have to at the end go to the data sheet. Again, we will always find that MOSFETs are the highest switching frequency devices, but they're also the lowest voltage range devices. IGBTs will be a little bit higher switching, higher voltages, higher currents, but slower. Controlled, GTOs. We talked about, controlled thyristors. When you can turn them off and turn them on at the same time. These will be, the next stage. Thyristors, which are, only semi-controlled. You can control only the turn on, not the turn off. They would be the highest voltage and the highest current devices. But their turn on and turn off times would be a lot higher as well. But the nice thing about thyristors is that when they turn off, when the current goes through zero, right? So we don't have this issue of loss anyway in the thyristor. So that's a nice, neat thing about thyristor converters as well, is their turn-off losses are negligible because you're turning off when the current's crossing zero. So V times I is nothing. So that's one advantage. But the problem is you cannot control the turn-off. If you want to turn off because you want to control ripple current, so that as soon as the ripple current, the current is falling, you want to turn on the device again or turn it off so that you maintain ripple. You cannot do that with a thyristor converter. You cannot, right? You don't have a choice. You will have, worse or less control on the power quality. That's the best engineering way to describe it. Yeah. Okay, so we discussed for your senior project. We discussed the converters that you can use. You can use the thyristor converter, no problem. But the performance will not be as good as another one where you have full control, right? Which chapter 8 we will allude to some of the inverter circuits that we talked about yesterday. So switching losses. We are concerned about this period now, where the currents are rising and the voltages are falling. Currents are falling, the voltages are rising. So this is the turn on of the device, and this is the turn off of the device, and this is when the device is conducting, right? So when the device is conducting, MOSFETs have a resistance, channel resistance, and current is flowing through the resistance. So you have V times I. There's a voltage drop, hence you have an I squared R, or you have a V times I power loss, right? So there's a conduction loss here in this period, in this zone here, and then there's a turn on switching loss, and then there's a turn off switching loss. Okay. We can try to use these exact waveforms and come up with these value or an equation for these quadratics here, quadratic curves, but too much. We don't like that. Power electronics people like no math. We like to simplify the world, so we will just figure out a way to make these look like all triangles, because then I want to know, because again, I want to know the switching losses, right? So this is the power loss curve. If I calculate the area under the power, it's equal to what? Area under the power for any physical phenomenon. If I have the power versus time, instantaneous power, what's the area under the instantaneous power curve? Come on. What's the area under the instantaneous power curve? What's the physical meaning of area under the instantaneous power curve? Area is the integration, right? So what's the integration of power? Energy, right? So if you have energy, and then you divide, if you have, so then I'm able to, if I calculate the area under this, curve here, I can calculate what? I can calculate the turn on switching energy. I calculate turn off switching energy, the conduction energy loss, right? And then if I take this energy and divide it by time, right, then I have what? Power. So I can, if I calculate this area, divide it by time. What time? This is happening every what? What? This is happening every time the device is turning on, right? So it's happening every switching period, right? Because it's happening every switching period. This is the turn on is happening every switching period. So every switching period, right? So you need to look at the losses every switching period, right? So what is your turn on losses? What is your turn off losses? What is your conduction losses every switching period, right? And that loss will be another constraint on your design, right? So you've selected a certain you've selected your inductors and capacitors, right? Based on what? How do you design your inductors and capacitors? You design them based on the curve, on the waveforms, areas under the voltage and current curves. These areas will be affected by switching frequency, right? Switching frequency or switching period, which is 1 over the switching period, will affect loss because I'm calculating the energy and dividing it by the switching period, or multiplying it by the switching frequency, right? So they're all interrelated. So that means that if you design your inductor and capacitor, thinking that your switching frequency is going to be something. Then I put another constraint on you to minimize power loss. What do you have to do? You have to go back and redesign inductor and capacitor, because you design inductor and capacitor for 10 kilohertz, for example. Then you went through your design. So you selected your inductor, you selected your capacitor, your switching frequency was 10 kilohertz, no problem. You found the switch that can do the job. You looked at the peak voltage across the switch, average current, selected the switch. The switch, you looked at its rise times and fall times. You added them up, and you saw that, okay, the rise time and fall time is, 100 nanoseconds, 1 microsecond, 1 microsecond. And you selected a switching frequency of 10 kilohertz, right? 10 kilohertz, 1 over 10 kilohertz is what? 10 milli, what? 10 milli, right? 10 milliseconds. So your rise times and fall times were 1 micro, we said, or 1 micro, or 100 micro, 1,000, 1 milli max, right? For MOSFETs, it will never be 1 milli or 1 micro. It will never be that. It will be in the nanoseconds range. Yeah, go to the data sheet we have. Here, it's the data sheet for a MOSFET. Rise times. T rise here. 100 nanoseconds. I want to zoom in. Right, T rise, 100 nanoseconds for the switch. Right, so T rise, 100 nanoseconds. T fall is 65. Fine, there's a turn off delay and turn on delay. Fine, add all the delays, the turn on delays and the rise times. Delays, that by the time you give the gate signal, the switch reacts because of the switch physics. There will be a reaction time, so there will be a time to charge the Miller capacitor in the MOSFET, and these capacitors to charge, and then the current to start rising. So they call that the turn on delay time. So add the turn on delay time, which you see here is what, 14 nanoseconds, and the rise time. That's why I just tell you, okay, rise time, and that's it, right? Because it's much bigger than the turn on delay time anyway. But you can add them both. Add 101 and 14, for example. This is the time that the switch will rise, the current will take to rise. And then time for the current to fall. You can consider the turn off delay if you want. It's fine. Here it's considerable. The turn off is typically more difficult than the turn on. Whether or not you consider it, as long as you show me what you considered, I'm happy, right? If you take 50 or you take 65 or you take 60 plus 55, fine. It doesn't matter. Just show me what you did and justify it, right? So let's say 100 and 100. Rise time, 100 nanoseconds. Fall time, 100 nanoseconds. So I'm talking about 200 nanoseconds. Versus, I said my switching frequency is 10 kilohertz. 10 kilohertz is equivalent to 1 over 10 kilohertz is, we said, what, 10 milliseconds, right? Or 100 micro, right? It's 100 micro. 1 over 10,000, right? It's 1, 2, 3, 4, 500 micro, yes. This is 0.0001. Put 2 zeros more. So you move the dot 6. So it's 100 micro, like I said. Okay, so it's 100 micro. So 100 micro is your switching period versus your switch needs to rise and fall in 200 nanoseconds. Right? So it's about 1,000 times less than your switching frequency. You're fine. Then you have time to control. You have time to rise and fall as if in the switching period, as if you don't, these times are zeros. Now you have full ability to control. Can you increase switching frequency? Increase it to, instead of 10 kilohertz, increase to 100 kilohertz. Right? So instead of 10, 100 kilohertz. So you're talking about what? 1, 2, 3, 4, 5, 6. So 10. Now you're talking about 10 microseconds is your switching period, right? So for 100 kilohertz switching frequency, 10 microseconds. 10 microseconds versus 200 nanoseconds. Still reasonable. So 200 times 10 is what? What? 2,000, right? So it's 2,000 nanoseconds. 2,000 nanoseconds is equal to how many microseconds? 2 microseconds, right? So 2 microseconds versus now my switching period, if I go to, my switching period now is what? 10 microseconds. 1, 2, 3, 4, 5, 6, yeah, 10 microseconds. Now it's getting close, right? For you to rise and fall, you need 2 microseconds. I only have 10 microseconds to play with, so this is a considerable part of my switching period. So I would say no. I would say this would be too much. Because you want to increase your switching frequency as high as possible, right? Why? Because you want to reduce the size of your inductors and capacitors, right? At the same time, you see that it's gonna affect switching losses. We saw that area under the curve of the power, you calculate that area divided by a switching period or multiplied by the switching frequency, which means that the losses are directly proportional to switching frequency, right? So you're gonna increase switching frequency to be able to reduce the size of the inductors and capacitors. At the same time, you hit your loss constraint. Your loss constraint will tell you, okay, no, you cannot increase too much because the switching losses and the conduction losses are all proportional to the switching frequency. I will show you right now. I'm not lying. I'll show you the equations here. But here, this would be cutting it too close. If you try to go to 100 kilohertz with this switch, I would say no. Right? And if you tell me, yeah, if you use it, fine, you may be able to use it, right? But if I tell you I want a duty cycle of 90%, you cannot do it. Or a duty cycle of 10%, you cannot do it. Because you're taking it's taking you 2%, it's taking you 2 microseconds to rise and fall. Out of the 10 microseconds, you've already lost 20%. You already lost 20% of your duty cycle. You have no control for 20% of the duty cycle. So that means that you cannot run at 10% duty cycle, and you cannot run at 90% duty cycle. So this would be not a good choice of switching frequency. If you tell me it's a good choice because maybe your required duty cycle for the buck boost converter or your whatever is about 50%, and this load is never changing, right? From your voltage transfer ratio, you require a duty ratio of 50%. Can you get 50% duty ratio with this? Yes, right? So fine, but if I tell you that this converter needs to operate from no load until full load, then this won't work, because if it operates at no load to full load, that I need to make sure that I'm operating the full duty cycle range, right? So depending on how the question is worded or how your design is worded, then it will change whether you can use this or not. You can use this for a power converter that has a fixed load that requires maybe 50, greater than 20% duty cycle, right? Because you already lost 20%. And it cannot be as high as 90%. So greater than 20%, less than 80% duty cycle. If you're operating in that range, you can use the switch. And it will be great because you can push the limit of your switching frequency to decrease your inductor and capacitor size. But then let's see what the next limit would be. The switching losses. We said that the area under the curve would be energy. Divide that by period, switching period, you will get the power loss. Switching power loss, switch on, turn on power loss, turn off power loss, and conduction power loss, right? So you either take the energy or the area under the curve divided by switching period or multiplied by the switching frequency. So how do we calculate this? We don't like to calculate too complicated things. So I don't like x squared. I only like first order differential equations. I like x times y, 3 times x. I don't like too much complication. So I like only straight lines, right? So how do I make this a straight line? Again, all of this is back of the envelope type calculations anyway, right? So what I can do is I can shift one of these with respect to each other, like here, right? If I shift them a little bit, so I don't make them both rise and fall at the same time, almost. I shift one a little bit and I shift the other a little bit so that, this is a straight line when this is rising, or this is a straight line when this is falling, right? So if it's a ramp times a fixed value, the sum is, or the result is a ramp, and then the result of this is, this is fixed, and this is falling. The result is also a straight line. Is this right or wrong? It's fine. It's okay. I mean, how long is this? How long is this taking? This is the rise time, right? This is the width of this is the rise time. How long is this taking? The width of this is still the rise time, right? You agree it's the rise time or not? This, the width here is, fine. This is the current rising and the voltage falling. So it's the rise time of my switch almost, because the current will rise and the voltage has to fall. This is when the switching period is over, right? So from here to here, this is the width here. It's also the rise time, right? So the width is the rise time. The top here, the width is the rise time. If I approximate this to a straight line, I have something like what I have in the bottom here anyway, right? The width is the same, so I can approximate this to a triangle somehow, right? The peak values that I'm multiplying by each other are what? Here I'm multiplying, okay, current is rising from 0 all the way to what? In the switches, in all our switches, our switch or diode currents, where average values was equal to what? Duty ratio, or 1 minus duty ratio times inductor current, right? So the peak value of this switch current is always what? Inductor current, right? The peak value is always inductor current. Whether it's the diode or the switch current, then it's either going to be D or 1 minus D, its average value. But its peak value is always the same. It's always the inductor current, okay? How about the peak value for the voltage? Peak value for the voltage in all our cases was the voltage across the two switches, right? For the buck converter is equal to V input. The boost converter is equal to V output. For the buck boost converter is equal to V input minus V output. So it's the voltage across the two switches. Always. It's the voltage across the two switches. That's always something we know, right? So here, what I'm doing is what? Here I'm keeping the voltage across the two switches and I'm multiplying it by the current waveform. The peak value here is equal to what? Peak value happens here. The peak value is what? Equal to what? What's the peak value of power? Instantaneous peak value of power. Inductor current is I multiplied by the voltage across the two switches. Right? The peak value is always the same. Inductor current multiplied by the voltage across the two switches. Right? So I know the peak value here. And I know the width here. And I've approximated everything to a triangle. So what's the area of a triangle? Half base times height. Right? So half the rise time multiplied by the height. The height is inductor current multiplied by the voltage across the two switches for any of the configurations. So this is the turn on loss. This will be the turn off loss. The half base, here the base is the fall time. Whether or not you include the fall delay time or not, I don't care. If you have a data sheet and you tell me you included it, just tell me you did and I will know. If you just include the fall time, not the turn off delay, it's okay too. Right? Again, I just want to know the process, that you understand the process, not that you have an exact number. Right? So this would be, the area of this would be half the fall time times inductor current multiplied by the voltage across the two switches as well. Right? So now I have a good approximation. And here it's just a rectangle, right? Here it's the rectangle. It's the inductor current multiplied by the voltage across the switch when it's on, which is, for the MOSFET, it's due to the resistance, the effect of the resistance. For the BJT type devices, it's due to the VCE across the device, the junction voltage, right? So you have, this is just the area of a rectangle. If you have this area, you multiply by the switching frequency, you get conduction losses. You have this area multiplied by the switching frequency, you get turn on switching losses. You have the area under this triangle multiplied by the switching frequency, you get turn off switching losses. Right? So this will be your other constraint. So let me write the equations for that, because they're not in the textbook. Okay, this is chapter 10 starts talking about losses, but in a lot of detail. I don't want you to read all chapter 10. There are just two sections of chapter 10 that's important. Yeah. So let's write the equations down. So the turn on switching loss, the turn on switching loss is equal to, we said it's the half base is the rise time, right? You can include the rise time delay if you want from the data sheet, that's fine. Half base times height. Height is the inductor current, IL in this case, multiplied by the voltage across the two switches. Okay? And then you do what? You either divide that by the switching period or multiply it by the switching frequency. Right? Because this was the area under the instantaneous power curve. Then you divide it by switching period or multiply by the switching frequency. So your turn on switching losses should be, of course, proportional to your switching frequency. The faster you switch, the more transition that you have within a certain, in a certain period of time, the more loss. Right? So the faster you do this, the more loss you have. So you need to make sure, if I tell you limit the losses, turn on losses to a certain value, that's going to affect your design. If I tell you, okay, now the turn off switching loss is equal to also half base, in this case is a fall time, times inductor current multiplied by the voltage across the two switches, multiplied by the switching frequency. This voltage across the two switches, guys, is equal to what? For the buck converter, it's equal to V input. For the boost converter, it's equal to V output. For the buck boost converter, it's equal to V input minus V output. Okay? Just three values. This will be whatever inductor current is. Inductor current may be the average value of load current, or maybe not. Right? Depending on the circuit. For the buck converter, IL is going to be the average value of source current. Right? Because the buck converter is here. Sorry, average value of load current. This is the buck converter, right? So inductor current, in this case, is equal to the average value of load current for the buck converter. For the boost converter, IL is equal to average value of source current. Exactly. So for the buck converter, it's equal to average value of load current. The boost converter is equal to average value of source current. For the buck boost converter, it's not this or not that. You have to know. You will be given your load. You'll be given load specs, for example, and maybe let's say I tell you this load is 5 watts, 5 volts, and the resistance is I don't know, 10 ohms, for example. Then you should be able to calculate average load current, right? You should be able to calculate the average load current. So if you know your average load current, then you know the average diode current. And if you know V input as well, from the voltage transfer ratio, voltage transfer equation, which relates V input, V output, and duty ratio, you know V input, you know V output, so you should be able to calculate duty ratio. From duty ratio, and the fact that you know that the current in the diode here is equal to what? 1 minus D times inductor current, right? So duty ratio is now known. You know the value of this. You should be able to calculate inductor current. For the buck boost converter, this is a bit different. Okay, so for the buck converter, it's average value of load current. For the boost converter, it's average value of source current. For the buck boost converter, you have to derive it. Okay, it's some value, but you have to derive it, yeah. Okay, so now we did the turn off, turn on, loss. How about what's left? Conduction loss. P turn off, so P conduction is equal to, we have a rectangle. This rectangle, or this rectangle has current flowing, right? There's current flowing for how long of your switching period? What is the ratio of switching period where you have the device on? Duty cycle. So right, your current will flow in the switch for the duration of the duty cycle. So for the duration of the duty cycle, so this for the duration of dt, duty cycle part of your time. So now I've calculated this time, this width, right? I need to calculate this height. So width times height is the rectangle area. What's the height? The height will depend if it's a MOSFET or it's if a BJT or IGBT type device, right? If it's a BJT or IGBT type device, what's the voltage across it? It's VCE, right? Times the voltage is VCE, right? I'm trying to find the area, right? This is the instantaneous power curve, P of T. P is V times I. Which V and which I? VCE times conduction current, which is this IL in this case. Whatever it is for the buck and the buck boost are different, right? So this VCE times IL, right? Multiplied by, same thing, switching frequency. Because this is the area under the power curve. This is the area under the power curve, right? This is the area, this is my instantaneous power curve. I'm calculating the area of this rectangle. It's this time multiplied by this height. This height is V times I. Okay, VCE times IL. Or for a MOSFET, it's what? It's RDS on times I to the MOSFET, I switch, average value. Right, so it's average value of switch current and actually not the average value, it's the actual value of switch current. Right? Instantaneous, I'm talking about, so it's RDS on times I switch. Actual value of switch current, right? So it's the instantaneous power curve. So it's I through the switch multiplied by the RDS on. right? So that's a voltage. Yes.
So this is not ESR, right?
What ESR? ESR is in a capacitor. This RDSR, the switch itself, a MOSFET has a channel resistance. Remember? So it's the channel resistance of the MOSFET multiplied by the current. So it's I times R is equal to the voltage across the MOSFET. Right? So that's the voltage across the MOSFET multiplied by the current to the MOSFET, which is equal to the switch current as well. So it's I squared times RDSR. Yes?
Why am I multiplying by switching frequency? You're not switching in the time of
Because this was your instantaneous power curve. Instantaneous power curve. We still have 4 minutes. Instantaneous power curve. We said that the area under the instantaneous power curve is what we have here, right? This is the area under the instantaneous power curve. The area under the instantaneous power curve is the integration of power, which is energy. Energy divided by time is the power, or multiplied by switching frequency, right? So now you've calculated all your losses. So now this is how your losses are going to limit your upper limit on switching frequency. So you've selected the inductor and capacitor. You wanted to make them as small as possible, so you kept boosting your switching frequency, pushing it higher, higher, and higher, making your switching period lower and lower and lower. Every time you go back and check the rise times and fall times of your switch to make sure that they are a lot less than your switching period. You check that, so you keep pushing your switching frequency. You keep pushing your switching frequency. That's going to increase your losses. If you don't have a limit on losses, no problem. You can put a freezer and cool your switch, no problem. But if you don't have the option of putting a freezer to cool your switch, then there will be a limit on switching loss. So that's, I really wanted to do this. I will introduce something and then we'll wrap it up. So this freezer concept is the thermal transfer stuff. So now you have losses. How do you know if your switch will burn or not? If your losses are going to raise the temperature, then your switch will burn. The losses will not raise the temperature of the junction. At the end of the day, you have a silicon inside the device, and inside this chip, right? Silicon chip inside the package. The silicon chip, if the temperature of that silicon chip is greater than the junction temperature, if you look at the data sheet that we have here, it will tell you here in degrees C. Okay, to tell you that this device can operate up to a junction temperature of 175 degrees C. If you operate higher than that, we don't care. It will burn. Right? That's what they're telling you here. Right? So how is this linked? The power losses are going to cause the temperature to rise. Right? How does this happen? It happens because of the thermal design of your power converter. So you have to make sure you understand that. That's where you select heat sinks. Or you select, a heat pipe. Or you select, these computers that come in with these heat pipes, these gaming machines that come with heat pipes. Why? It's because of this. The temperature is rising, so you have to cool it somehow. So you have to select a cooling system. This cooling system will have a way to dissipate this heat. If you're able to dissipate the heat, fine. Burn more power. Burn more power as long as you can dissipate it. If you cannot dissipate it, what's going to happen? You have something enclosed and it's burning power inside, and the heat is not being conducted to the external environment. What's going to happen? Temperature will keep increasing. If you're able to conduct, no problem. Everything's fine, temperature will not increase. But if you're not able to conduct, then the temperature will keep increasing. So just 1 minute, and then we'll do this next time. So the way we will model this is as follows. We will have an electrical equivalent to the thermal system. So we want to make sure that we operate at a certain junction temperature. So this will be my junction temperature node. My device, my silicon junction here, my silicon device, is inside a package. Inside the package. Right, this is my device. It's inside the package. This is the problem I'm worried about. This thing getting hot. This package can have a thermal pad at the bottom, like a metal pad at the bottom, which can help dissipate. This device can be a plastic package, very difficult to dissipate. This device can have a package that's this big, or it can be this small. If it's big, it's nice. Large surface area can dissipate. If it's small, small surface area cannot dissipate. So there's an impedance to heat flow from the case to the junction, or from the junction to the case. So that's the thermal resistance from junction to case. That's a resistance to heat flow. So if I have power loss, so this, my current source is power loss. My power losses will cause what? If temperature to rise. So here. I will draw this very quickly and we'll continue next time. So this will be my junction, this will be my case, this will be my sink, and this will be my ambient, right? So think of it this way. If your current flows, you will have a certain voltage here. This is ambient temperature. What is it? 20 degrees C, for example, right? And then current will flow. It will cause a voltage drop. What's this temperature now? This ambient temperature plus the drop across this resistance. This is going to be some value. Then here you have the temperature at the sink, at the heat sink. Here, temperature at the case. Here will be the temperature at the junction, right? So your power loss is now going to dictate the temperature at your junction. So we'll do an example on this next time, okay? So now this is the end of the power converter design.